Welcome to this lecture module on optics. So far we have discussed about formation of images by lenses, in particular initially by mirrors and then by lenses, and we will now move on to optical instruments where these principles that we have studied and the lens formula that we have derived will be applicable, will be useful. So, today we will see the topic of viewing objects. So, viewing objects, eye as an optical instrument. Now, some facts I have jotted down here, so that I do not miss those facts. So, viewing objects, objects are viewed or seen through the eye. Eye here refers to the human eye. Eye is one of the finest organs which functions like an optical imaging device. An image of the object is formed on the retina. I will show you a schematic of the human eye, which is then perceived appropriately by the brain. Now, there are certain limitations. The limitations are when the object is very far, like celestial bodies, stars, distant galaxies, when the object is very far, or when the object is very small microorganisms and very small objects, and then eye needs some optical instruments to assist in viewing. So, that is what we mean by viewing objects and the need of optical instruments. So, optical instruments, in particular we are interested in microscopes and telescopes. So, optical instruments, microscopes and telescopes are optical instruments that assist the human eye in viewing very small, micro standing for very small, and far away objects, far away, tele means at a distance or at a remote place. So, far away objects respectively standing for microscope for very small and telescope for far away objects respectively. Eye also needs assisting devices to correct defective vision, such as far-sightedness, which is also called hypermetropia or even hyperopia, and nearsightedness or myopia. To understand the above, that is functioning of a microscope, telescope, and what do we mean by these defective vision, it is necessary to know first the constitution and functioning of the eye. So, let us see the eye as a imaging device. So, here is the human eye, a schematic of the human eye, or which we call as this the eyeball. So, what we see here is the cornea, here cornea, it is a transparent membrane, and here is the retina, which is the image sensing receptor. So, this is the light receptor which acts like the image sensor, and here is the eye lens, the most important lens, eye lens, and what is shown here is the iris. Iris is a diaphragm or a membrane with a hole, and the hole size here can be adjusted. Eye adjusts itself depending on the intensity of light that is incident, or depending on the ambient light. Iris, the diaphragm, adjusts the hole size from anywhere from 2 millimeter to 8 millimeter. So, iris is the diaphragm, adjustable diaphragm, and both the chambers here are filled with a liquid, a transparent liquid. Here the liquid is called aqueous humor and the transparent liquid is called vitreous humor. The refractive index is approximately 1.36 and the eye lens has an approximate refractive index of 1.40. It is a little harder towards the center and more softer towards the edge, and the average refractive index is approximately 1.40. An important component here is the ciliary muscles which are attached to the eye lens. The muscles can these can stretch or compress they get extended or they get compressed, which will pull the lens, which also stretches the lens. The lens can be stretched, which means the radius of curvature of the lens will change depending on the tension in these ciliary muscles. When they are relaxed, then the lens is fully stretched, and when they are stretched, that is stretched in this direction, stretched or compressed, then the lens radius of curvature changes. This has a very important role in the human vision. Now, retina is the optical receptor, as I already pointed out. Retina is the optical receptor where the image is formed. The object which is in front of the eye, here is the lens, and the image is formed on the retina. It comprises of a large number, millions of optical guides called rods and cones, which are then connected to the optic nerve, which carries the signal to the brain, and the signal interprets, signal perceives, the brain perceives based on the signal the type of the object. Now, first, as I mentioned, that the lens, the eye lens, so let me draw it here and show. The eye lens is attached or linked to the ciliary muscles. So, these are the called ciliary muscles, ciliary muscles. The muscle can stretch the lens. So, this can stretch, which means the lens, let me show it here, the lens would get stretched like this, because if it is getting stretched in this direction and this direction, what happens, the main thing that we need to see is the radius of curvature has changed. The radius of curvature has become larger, which means the focal length has become larger here. Or the muscle can get contracted, which means the lens will further reduce. So, it will bulge more like this. In this case, the focal length will decrease. So, focal length will decrease or focal length will increase depending on the stretching or contraction of these ciliary muscles. And therefore, the lens, eye lens, so this is the eye lens. So, eye lens, this is an important point to know, that eye lens has a flexible or variable focal length. We will discuss more about this a bit later. Now, this variation in the focal length, so that the image is always formed. Please see, if I continue this here like this, there is the retina here at the back, the retina is here, and the image is formed on this retina, because this distance is fixed depending on where the object is, the focal length of the lens has to be adjusted, so that, so let me just show as an example, that if the object is here, then it forms an image here. Now, depending on the position of the object or object distance u, the focal length will get adjusted, so that the image is always formed on the retina. And this process of adjusting the focal length is called accommodation. So, let me show you a pre-drawn figure, a nice figure here. So, accommodation, what is accommodation? So, this is a very important process. So, what I have shown here is parallel light, which is focused here at the point in a normal lens. This is what we have studied. In a normal lens, the radius of curvature is fixed. So, focal length is fixed, and therefore, parallel light will get focused at the focal length. Focus, f is the focus, and therefore, this distance is the focal length. If the object comes closer to the position O1, then the image will be here. So, we know that how to find the position of the image by using the lens formula. If the object comes even closer, then the image will form here. So, the image is formed at different locations, or the image planes are at different locations depending on the position of the object. Now, if you come to eye, so what is shown here is the eye lens. First, let us look at the parallel rays as here. It gets focused on the retina here. Now, when the object comes closer, I have taken one position here, object position, a point object here, then unless the focal length reduces, the image would have come outside, image would have been focused somewhere here, the image plane where the image is formed would have been outside, but now the lens compresses. That is why I have shown a second lens. Actually, it is the same lens, but for the second situation the lens gets compressed, so that the radius of curvature becomes smaller and hence the focal length becomes smaller, and therefore, it becomes smaller, so that the image again forms at the same place on the retina, and this is called accommodation. The lens accommodating itself, so that the image is always formed on the retina. The image is focused on the retina. Of course, there are some limits that for any distance the lens cannot adjust, there is some limit up to which the lens can be stretched, and one can accommodate this. Now, accordingly, there are two important distances which are called near point and far point. So, we will see what is this near point and far point. So, here again I have illustrated what is this near point and far point. Parallel rays of incident on the lens. So, this is the reduced eye which I have shown for simplicity, this is the eyeball and this is the eye lens. So, it is the reduced eye. Henceforth, we will only show this not with optic curve, optic lens and all those optic nerve and so on, simply show the lens and this is the eyeball. It is understood that it is filled with liquid here. So, this is called reduced eye. So, I have showed here reduced eye. The image distance V is always fixed, V is fixed, and the image is always focused on the retina. So, the reduced eye filled with the vitreous humor. So, here P n is the near point, meaning, so far away objects are focused here. As the object position comes closer, closer and closer, and P n, when the point object is here, then it still focuses on the retina. But if you bring the object at a distance smaller than this capital D, what is capital D is the distance here to the near point, P n is the near point, capital D is the distance to the near point. When the object distance is less than D here, then it is no more able to focus the image onto the retina, the image is formed outside. So, then what is near point? Therefore, P n, the near point, is the distance, near point is at a distance D, that is the least distance for clear vision. If the object comes at a distance less than D, then the object will not be clear, because the image is formed outside the retina, which means on the retina we will be able to see only blurred images. The image gets fuzzy or blurred on the retina when you come below the near point. Similarly, similar definition for far point. Far point is the maximum distance. For normal vision, we will see that the far point is at infinity. In other words, any object at a very far distance will be focused on the retina. But there are certain persons with certain defects where there is a far point. He or she may have, the person may have a far point somewhere here, which means this only objects from here to the near point will be focused, and objects beyond that will not be focused, and that is called the far point. So, far point is the maximum distance for clear vision, near point is the least distance for clear vision, and far point is the maximum distance for clear vision. So, we will discuss this more in the next slide. So, in a commonly for normal vision, D is approximately 25 centimeters for normal vision. For normal vision, D is approximately 25 centimeter. Actually, this varies from person to person and this varies with age even for the same person. For example, for children around 10 years of age, so 10 years, D is, so this is, I am just giving some typical number, age and D. D is approximately 10 centimeter, which means objects which are as close as 10 centimeters will also be seen very clearly by young children. But those who are in the range of 20 to 25 years, these are approximate ranges. D is also approximately 25 centimeters. Those who are in the range of about 60 years, then this could be anywhere from 100 centimeter to 500 centimeters. D is the distance for clear vision. So, objects which are closer to them are still visible, but they are not visible clearly. The fine features of the object will not be distinguished. So, this is for normal vision, and for normal vision the far point, that is P f, the far point is infinity, far point is infinity, which means the eye can be focused to infinity. Infinity here refers to a very large distance. So, eye can be focused, eye can be focused to infinity. Which means that objects which are at a large distance are also clearly visible, and therefore, for normal vision far point is infinity and near point is approximately D is equal to 25 centimeter. This has some important implications subsequently when we discuss about microscopes and telescopes. So, let me now discuss briefly the two defects, common defects in vision, although we will not go into the details because it is beyond the scope of our course here, but we would like to see what are these two defects. These are very common, and therefore, the first one is nearsightedness. I have just illustrated this. So, the diagram, so here is the eyeball, the reduced eye, this is the far point. For the person with nearsightedness, I have already mentioned that the far point is not infinity, but at a finite distance, and that distance is P f here. P f is the far point for the person with the nearsightedness or myopia, and the near point is somewhere here, which means all the objects in this range the person is able to see clearly, which means all the objects which are here are clearly focused on the retina here. However, objects which are farther than this here, I have shown with the red color here, O is focused at the image point here, which is not on the retina, and therefore, on the retina there will be a blurred image, because the rays will continue like this. So, the rays will continue on the retina here. So, it is not focused on the retina, and therefore, on the retina the image will be blurred. Now, a simple way to correct this is use of concave lens to correct nearsightedness. So, this object which was at a point O, which is not focused on the retina, but inside, can be made to focus on the retina by giving some additional divergence by using a concave lens. By giving an additional divergence by use of an appropriate concave lens of appropriate power, one can provide sufficient divergence so that the object is again focused onto eye, and therefore, nearsightedness is corrected by the use of concave lens. Now, the other important defect is the farsightedness. So, it is again illustrated here, the farsightedness is here. I have taken several points here. Far-sighted means the person can see things far off very clearly, but those which are nearby he or she will have difficulty in seeing them clearly. So, what is shown in the diagram here is the blue lines, which are parallel rays, are focused on the retina. From the P near, his P near is here, which means up to this point all the objects are focused clearly on the retina. However, objects which are nearer than this P n, as I have already said that this distance to P n varies from person to person, it could vary anywhere from tens of centimeters to hundreds of centimeters depending on the age of the person. And therefore, an object which is nearer than the near point will get focused outside here, image point is here. This object O is focused image at the image point, which means on the retina it is not focused, and therefore, he or she will see a blurred image. And obviously, this can be corrected by use of a convex lens. So, because the lens was not able to focus it here, you need some assisting device to focus it further. Lens is able to focus somewhat, but not able to focus it strong enough so that the image is formed here, and therefore, the convex lens helps in focusing the image back onto the retina. So, using a convex lens to correct farsightedness. Now, we will not go into the mathematics and details of these, but what I would like to discuss, so far I have considered point objects. What about extended objects? How to see image formation of extended objects in the eye. So, we will see this now, image formation on the retina by extended objects. First, I am recalling what we have studied. Normal lens, object is here, we take two rays. So, let us focus on the normal lens. So, here, so there is the object, we take the parallel ray passing through the center, the intersection gives us the image point, and this is the image distance and this is the object distance. Here is the object distance. For this object distance U1, the red colored rays I have shown here form an image at I1. So, intersection of the two rays, because focal length f is constant for a given lens, for a normal length f is a constant, and therefore, use lens formula to get V. Two rays are necessary to determine image distance and size. The distance to the image point and the size of the image is determined by use of two rays, any two rays. We have discussed this in detail. Now, let us see the eye lens. So, here is the reduced eye with the eye lens here. The image distance here is fixed, unlike here image distance is fixed, and therefore, we do not require two rays to locate the position of the image. The position of the image is fixed, it is only the extent of the image, the size of the image that has to be determined here. So, the size is determined by the angle here, the angle subtended at the eye will tell us what is the size of the image on the retina. The retina is like a fixed image plane. Here the image plane varies depending on the position of the object, but in this case the image plane is fixed, but what varies is the focal length of the lens, adjustable focal length. Here f is constant, here adjustable focal length, but fixed V, and therefore, only one ray is sufficient to determine the image size. The size of the image, which refers to the angular extent here inside the retina, this will determine the size of the image. And therefore, in the subsequent discussion we will consider only one ray. It is not practical or not necessary to consider two rays, because we must remember that this size here, the iris is only few mm's and we are observing big objects. So, there is no question of drawing a parallel ray to a small hole, and it is not required, and therefore, we will discuss with only one ray, the extreme ray, the ray from the tip of this object, extreme end will determine the extent, the maximum extent of the image here, the size of the image. In angular terms, the size of the image is determined by the extreme ray. So, it is sufficient for us to consider only one ray. Now, let us discuss the image size and angular extent and how accommodation takes place and how imaging takes place by the eye. So, here what I have shown is object size versus angular extent on the retina. First, the same we have considered the same object position, but objects of different height. Here I have illustrated considering 3 different objects of height h1, h2, h3 at the same position. What is shown here is the angular extent for the 3 objects are different. Larger the object, that is larger size of the object here corresponds to a larger angular extent on the retina. So, larger objects subtend larger angles at the eye here. So, we can look at the angle here or the angle here, it is one and the same, because we are looking at the central ray passing through the center point of the lens, and therefore, angle subtended here is the same as angle subtended here, and therefore, larger the angle subtended, larger will be the area of the retina which is involved. So, this whole region is the retina. So, retina comprises of millions of cones and rods which are optical sensors. So, sensory components there which are linked to the optic nerve which carries the signal to the brain. Now, larger the area occupied here, the angular extent here determines the area occupied on the retina, and therefore, the number of rods and cones involved in sensing this picture, in sensing this image. So, larger area occupied by the image on the retina, better resolution and clarity of the image, because larger number of rods and cones would be involved in the perception of the image. Now, this is first I have considered same object position and different sizes. Now, let us see the same object size, but different object positions. What is the effect? Here B, same object, therefore, the size is the same, but different object positions. Object which is nearer subtends a larger angle, and the same object as it goes away, it subtends a smaller angle at the retina and at the eye, which means the same object is seen or sensed by smaller area of the retina, which means smaller number of rods and cones, smaller number of sensors here, as compared to a larger number of sensors in the case of the same object when it comes closer. And therefore, when it comes closer, of course, we are looking at distances beyond the near point, so that the object is still clearly visible, but the area occupied here on the retina is larger. So, the point, the same object at different distances will subtend different angles at the eye. Angle subtended will determine the size of the image on the retina, and hence size of the object as perceived by the brain. So, the object which is closer will appear bigger compared to the object which is far away, although it is the same object or object of the same size. The angular resolution of the eye is about 1 arc minute. The angular resolution here refers to the angular resolution refers to the minimum angular separation which can be sensed by the eye. So, let me discuss this a little bit more, the 1 arc minute angular resolution. So, here is the eye, a distant object here, there is a object. So, maybe sun or moon here. Now, this subtends an angle. So, this is the diameter d, let me use small d, and at a distance L. This is angle theta, the same as the angle theta here. Now, therefore, theta, so d is equal to L theta, or theta is equal to d by L. So, as L increases, d becomes smaller and smaller and smaller. For example, we can calculate what is this theta subtended at the human eye. So, this is the human eye. So, this theta can be calculated, and this theta would come out if you substitute the diameter of the sun and the distance of the sun, this will come out approximately 10 to the power of minus 2 radians. Also the same for this theta, which is also the same almost for the moon also, for the moon and sun, approximately this. That is why we can see sun and moon very clearly, because eye resolution is 1 arc minute. So, 1 arc minute, which is approximate, which is equal to 1 by 60th of a degree and pi by 180 radians. So, this will be approximately 3 into 10 to the power of minus 4 radians. And the theta subtended by moon is 10 to the power of minus 2 radians, and that is why we can see moon very clearly, because the angular resolution is a more involved subject, involved topic, but it is sufficient for us to know that so long as the angle subtended by the object at the eye is larger than the minimum which I can resolve, I will be able to see the object clearly. For example, using the same formula, theta is equal to d by L. If you calculate this for stars and galaxies which are further away, millions of kilometers away, then we will get theta which is smaller than 1 arc minute, and that is why eye is not able to see those stars which are very far off. But we know that we can see these by the use of telescopes. So, we will come to telescopes shortly, maybe in the next class, and this is what is meant by the importance of angle subtended at the eye. Now, both what we have seen, therefore, both very small objects. So, this is, so both very small objects which are nearby, small objects nearby will also subtend very small angles. So, what I have shown is large objects like sun or moon, celestial bodies which are far away also subtends very small angles, but small objects. So, again let me show the eye here, and a small object which may be very close, like a micro is a very small pin or something, then that will also subtend a very small angle here, and that may be less than the angular resolution here. For example, if I have this size d is equal to 1 micrometer, and even if you keep this distance is equal to, let us say, 1 centimeter or 25 centimeters minimum that I can see, then you can immediately calculate theta is equal to 1 micrometer, that is 1 into 10 to the power of minus 6 meter. So, let me write in meters. So, 1 into 10 power minus 6 meters, and 25 centimeters is 0.25 meters, and therefore, what you have is this equal to 4 into 10 to the power of minus 6 radians. Obviously, so this is much less than the resolution of the eye. In other words, a 1 micrometer sized object will not be, eye will not be able to see. A quick calculation here. So, the point that I am making is both objects which are far away and objects which are nearby, but small objects will subtend angles which are smaller than the resolution of the eye, and I would not be, the naked eye would not be able to see these unless there are some assisting devices. And our next interest would be to see these assisting devices, which are microscopes and telescopes. So, here it is. So, far away objects subtend, the angular resolution of the image will be poor. Now, therefore, can we somehow increase the angle subtended at the eye by the small objects and far away objects, so that we can see them clear? The search for solution of the above question led to the development of microscopes and telescopes. So, first let me discuss the simple microscope, which is the magnifying glass, a convex lens as a magnifying glass. So, here it is, use of convex lens as a magnifying glass. This is the simple microscope. This is simple. Obviously, we will also study the compound microscope, and so first let us understand the working of a simple microscope. So, what I have shown is the eye ball here with the eye lens, a small object of height h which is placed at the near point D subtends an angle theta 0 here or here at the eye, which is equal to h by d. D is the distance to the near point. As I mentioned, we normally take this as 25 centimeters, and the angle subtended theta 0 is h by d. H is the height of the object. If I bring the same object closer, the same eye, so there are three figures here, figure 1, figure 2, figure 3. So, we can see them one by one. So, first here we have seen this an object which is at the near point, but the object is very small, it is subtending an angle theta 0 equal to h by d. Actually, theta 0 is very small. So, we have used the approximation tan theta 0 is equal to theta 0. Now, if we know that the angle subtended at the eye has to be larger if we have to see the object more clearly. And how can we do that? If we bring the object closer, it will subtend a larger angle because the distance becomes smaller. So, that is what is shown here, that if we bring the object closer, then angle becomes larger. Bringing the object closer, angle increases, but the image is not clear. The image is not clear because we are below the near point. The near point is here, and we have brought this closer below the near point, and eye is not able to focus it, and therefore, the image is not clear. Now, at this stage in figure 3, what we have done is we have introduced a convex lens in between. The object position is the same, but we have inserted a convex lens as a magnifying glass. So, what is shown here is the formation of the image. We have positioned the lens such that the object position is close to the focus, a little less than the focus, so that this forms, we have already studied this, that this forms a virtual image and magnified virtual image. So, what is shown here is a parallel ray passing through the lens and through the eye lens, forming here the image, and this one passing through, again forming the image here. Now, note that this subtends an angle theta to the eye. There is an angle theta subtended, which is the same on both the sides here, theta at the eye, and the image also subtends an angle theta dash. But both theta and theta dash are nearly equal, because we can see that the rays are almost parallel. In fact, if we place the object exactly at the focus, then the image will be formed at infinity. So, what has been done is the lens has been introduced and held or positioned in such a place, so that the virtual image is formed at the near point. If the virtual image forms below the near point, again it will not be clear. The virtual image may be formed anywhere at the near point and beyond. So, to have this virtual image, the object position should be close, but a little less than the focal length, and f is the focal length of the lens. Therefore, theta dash here can be written as h, the object height, divided by the focal length approximately. So, that is what I have shown here. The same figure I am showing here in the next diagram, so that it is more clear, the calculations are more clear. So, here is the object, a small object, a micro object which the eye wants to see, and the lens is introduced here, and therefore, we see h by theta dash. So, theta is nearly equal to theta dash, theta here is nearly equal to theta dash, because these two rays appear to come from a point here. So, this is this dash dotted line is appear to come, there is no actual ray, actual rays are these two which look almost parallel, and therefore, this angle is nearly equal to this, and therefore, theta is nearly equal to theta dash is equal to h by f. The m theta angular magnification, m theta is defined as theta with in the presence of the lens divided by theta 0 without the lens for clear vision, that is h by f. So, we have seen that when the object was placed at P n, theta 0 was h by d. So, that is the minimum distance at which it can be placed and seen clearly, whereas the angular magnification is given by theta divided by theta 0. Theta we have already seen is h by f, and theta 0 is h by d, and therefore, m theta is equal to d by f. The angular magnification is d divided by f. F is the focal length of the lens which is introduced. From the diagram, we can also quickly see the linear magnification. We have studied this, how to determine the linear magnification. M is equal to h dash by h. So, this is the size of the image, size of the object, which is equal to v by u. So, v is u is the object distance here, is shown here u object distance, which is very close to f u, and v is here, that is at d. So, we have placed the lens such that the virtual image is formed at the near point. Therefore, v is nearly equal to d. The near point is the distance d away from the eye, which is 25 centimeters, and the virtual image is formed approximately here, or maybe a little further. Therefore, the linear magnification is equal to v by u, which is equal to v divided by u. U we can write as from lens formula 1 by v minus 1 by f, which is equal to 1 minus v by f, because v is minus here negative. So, 1 minus v by f, f is positive for the convex lens. So, only v is negative, and therefore, this is 1 plus d by f. The linear magnification is 1 plus d by f, and the angular magnification is d by f, approximately, very good approximations there. When the eye, as I mentioned, when the eye is focused to infinity, that is when the object is exactly placed at the focal length, the two rays run parallel, so that the image is formed at infinity, theta is exactly equal to theta dash. Right now, theta is nearly equal to theta dash, is a good approximation, but theta is exactly equal to theta dash is equal to h by f for small values of theta. I focused at infinity, we may quickly recall that I focused at infinity means we have the lens here, and this is the focal length, and therefore, the object is placed at the focus here. So, we have a parallel ray coming here. So, there is a focus here, which means at the same distance the second focal length here. So, this is f1 and f2 we recall, and the ray would pass like this through the focus, and we take a parallel ray which is also passing from here. It is the ray passing through this center point, and they will turn out to be parallel, because this distance is the same as this distance, this height is the same as this height. So, these two rays appear to come from a very large distance, and if the eye is here focus to infinity, is called focus to infinity. So, it is the eye lens focus to infinity. then theta, the angle subtended here, theta dash, which I had denoted, is the same as the angle which is here, theta, which is the angle subtended at the eye. So, that is about the functioning or working of a simple microscope. So, we have the angular magnification m theta is equal to d by f, d for normal vision, d is approximately equal to 25 centimeters, and in practical cases, practical lenses have focal length. Of course, the angular magnification will be larger if the focal length is smaller, because this is fixed about 25 centimeter, but f smaller the f, larger will be the angular magnification, but in general f cannot be reduced beyond, for practical reasons it cannot be reduced beyond a certain limit, and therefore, f is generally about 3 to 4 centimeters. So, if you substitute 3 centimeter or 4 centimeter here, so 3 centimeter, so this will be equal to 8.3. If you substitute 4 centimeter, this will be equal to 6.25. So, m theta is equal to 8.3 for 3 centimeter, and f is equal to 4 centimeter. In other words, the magnification, angular magnification is typically in the range of 5 to 10 or 5 to 8. So, 5 to 10 for practical magnifying glasses. This is not sufficient, as we know that when we want to see very small objects, microscopic objects, then this kind of magnification is insufficient, and the simple microscope which uses only a magnifying lens will not be helpful to us, and we need to go for the compound microscope. This will be the topic of our next lecture. Thank you.